Good morning, everyone. Thank you for coming to this session. My name is Huijuan Meng, and I'm a senior psychometrician at Graduate Management Admission Council. Here, I would like to thank my co-author, Chris Han, sitting over there, for his valuable input to this study, Comparison of Pretest Item Calibration Methods in CAT. Actually, this is an old research area. From the first day CAT has been used by the testing organizations, pretest item calibration became a topic kept haunting researchers. It was revisited again and again under different RT models with different calibration methods and using different tools. This task is challenging because of the specific nature of CAT data. All scored items are adaptively administered to students, so we end up with a huge sparse matrix with a restricted ability range for operational items. This creates issues for commonly used pretest item calibration methods, such as fixing operational item parameters in the calibration, or freely estimating all items and then conducting a linear transformation based on two sets of parameter estimates for the operational items. Fixing person parameter method is less popular. Despite its simplicity and conceptual attractiveness, very few testing programs adopt this approach. This method actually was originally proposed by Stocking in late 80s, but practitioners probably have concerns about using theta estimates as their true values in the calibration. And another possible reason for its being less popular is that calibration tools for 2PL and 3PL models, it was not implemented in most softwares. And also the user manuals didn't provide details for for this process. I saw this feature is being implemented in Logist and its replacement by LogMG and IRT Pro. But still, if you look at the manual, it's only like a keyword, not too much technical details, which may further discourage practitioners from using this approach. In the newly developed software FlexMERT, authored by Professor Cai Li in 2013, we happily saw that both fixed item and fixed person parameter calibration methods have been implemented, which allows us to systematically compare them for CAT pretest item calibration. And So in our study, how these two methods perform is one of our research focuses. Another one is about the impact of population change. Just as other testing organizations who also deliver exams globally, in recent years, we observed that the volume of our international students is increasing significantly. And they score, on average, they score higher in the quantitative skills than the US students, in the domestic students. So we would like to see how robust these two methods are when we have this population ability change. So here is the design. Calibration method and ability level are two major factors. And low ability level contains the largest proportion of domestic students. And the theta mean is about 1, which is closer to the item pool B parameter mean, which is 0.35. And we also include the three factors: exam length, calibration sample size, and IRT model. Our data is generated under the 3PL with a fixed C model, and C is set to be 0.2. Theoretically, this model is a special case of 3PL, so the result should be about the same theoretically, but let's see if that's the case. Before comparing the item parameter recovery accuracy, we look at calibration convergence and stability results. So if either test failed, we should be cautious about using estimates as their final values for future scoring. And so here is the results for the mean factors. The horizontal axis, we show values for each factor. So calibration method, we have fixed item. And for fixed person parameter estimation, we include two sets of results. One is like we use estimated theta in the calibration. Another, we use the true theta to see how much they differ. And then ability level, we have low, medium, and high. And with the low ability group, is closer to the with the closest distance to the item pool difficulty. And exam length, short, medium, long, and sample size and IRT model is the last one. The vertical scale is calibration convergence and the stability success rate. The higher, the better. So we first look at the results for calibration method. And as you can see, fixed person parameter estimation has have a higher success rate than the fixed item approach by about 5%. And for ability level, low ability level, we have a higher success rate, and so which means the closer distance we have between between ability and the difficulty mean, and the higher success rate we have. And for exam length, shorter exam has a higher rate, which means the shorter the exam we have, the better results we get in terms of convergence and stability, which is is a little bit surprising, this result. And so we just look at another factor, the sample size. This one is as what we predicted. The larger sample size help improve the results. And finally, we have the IRT model. The one we used to generate the data has a slightly higher rate than the other one. But a higher convergence rate does not necessarily mean a more accurate results. So when we look at exam length, actually, this is ICC diff. It were computed using both true and estimated item parameters. And then here, shorter exam, although they have a better convergence and stability success rate, it actually shows larger difference, ICC difference, than the longer exam. And for calibration method, the results is pretty consistent to the previous one. Fixed person parameter estimates has a smaller difference between true and estimated ICC results. And the ability level, the pattern is also clear. Low ability group has a shows smaller difference between true and the estimated parameters. And the sample size, again, larger sample size has a better results. And for IRT model, they have pretty similar results. We also look at IRT A, B, and C parameters separately. This figure is for root mean square error, and this one is for mean bias error. And we have these factors, along the horizontal axis. So for some reason, although we have a better, for fixed person parameter estimation calibration method, we have better results for the ICC. But if you look at IRTA, for some reason, this method has a larger errors for this parameter. And also, it shows larger mean bias error as well than the fixed item parameter estimation calibration method. And for ability level, after rounding the results to the second decimal point, they show pretty similar, about the same results across three ability levels. And exam length, the results are consistent to previous one. The short exam yields larger errors than the longer exam, and the sample size is the same. Large sample size improves results. And finally, the IRT model misfit, this one with 3PL contains larger errors for A parameter calibration. And when we look at IRT-B results, for these three factors, the pattern are consistent to what we have for IRT-A parameter. So short exam, smaller sample size, and IRT model misfit, they are all associated with larger errors, estimation errors. But for the calibration method, the order is reversed. Here we have better results under the fixed person parameter calibration results than the fixed item approach. And for the ability level, again, low ability level contains smaller estimation calibration errors. And then again, this low ability group is the one contains the largest proportion of domestic students, which has a better alignment to the item pool difficulty level. And for IRTC parameter, we dropped the last factor because in the calibration we fixed the C value for that model. So the other four factors, again, all the patterns, the results are consistent to what we observed for IRTB. Like fixed item approach has larger error and a low ability group, longer exam, and the larger sample size. They all help improve the calibration results. So we also look at the interaction effect, and for time's sake, here we only look at the weighted ICC diff, and so the column, it's hard. I know it's hard to see. So the column we have is for the exam length, the factor. So this one, is for the short exam with only 15 operational items. And this one is the exam with the median length, and the operational items is 25. And then the last one is the long exam, which contains 45 operational items. And the row corresponding to ability level. So the first one is low ability level, medium, and high. And these three values corresponding to the sample size, small, medium, and large. So, and we use this blue circle to represent results from fixed item parameter calibration approach under the 3PL model. And this red triangle is fixed item as well, but under 3PL with a fixed C parameter model. And this star is a fixed person under 3PL, regular 3PL model. And the last one, the green one is for the fixed person under 3PL with a fixed C, the one we use to generate data. So when we look at the short exam, and these two on the top, there are the results for fixed item parameter estimation calibration method. And then the bottom two lines are for fixed person calibration approach. So as you can see, as the ability shift is getting bigger, the difference, the performance difference between these two calibration methods is getting larger. And then, these two are for the fixed person parameter approach, and these two for fixed item parameter approach. And then, as we have a longer exam getting longer, the difference is getting smaller and smaller. Meanwhile, when we look at sample size, the larger sample size, within the method, the larger sample size, help improve the results. But between the method, they actually increase the performance difference. And then, so this is exam length, and then this is ability. So, but as the exam getting longer, as you can see, the difference, is getting smaller and smaller, and it's become unnoticeable, except for this one, for this when we have big ability shift, and then those differences still exist, even with larger sample size, even with longer exam. So in summary, findings in these results suggest that fixed person parameter calibration results use more accurate estimates, and it also has a higher convergence and a stability success rate than the fixed item parameter method does, except for LLTA parameter. For some reason, these fixed person parameter calibration methods tend to underestimate LLTA parameter, even when we use the true theta in the calibration. But given the overall performance of fixed person is better than the fixed item parameter calibration method, we should we should further investigate the causes and try to identify an effective way to correct this tendency. About ability level, this ability shift adversely affect the calibration accuracy and the calibration success rate. But compared to fixed item parameter approach, fixed person method is more robust, especially for short exam and with a smaller sample size. And exam length. This factor actually led to mixed results. The longer exam we have, the more accurate results, parameter estimates we obtained. But it also shows lower convergence and stability success rate. So, we in the operational work, if this success rate is lower, the chance for us to fail the calibration is bigger. So we should be cautious about the specific methodology we use for the calibration. So this one is pretty critical when you make operational decision about the method we're going to use. And the calibration sample size result is consistent with the findings in the literature. The larger the better, and also the higher convergence and the stability success rate. And finally, for LLT model, when we free RTC parameter, presumably the results should be about the same because one is special case of the other. But actually, we observe that both A and B parameter estimates, are less accurate than the fixed the fixed C parameter, the one we use to generate data. So was that caused by the model or by the CAT data, or maybe by both? We were not sure, but probably we'll conduct a follow-up study to further check, this model misfit. Actually, it's not misfit. This model change on the calibration results. So for future research, in addition to the two topics I just mentioned, we should also compare flex merge results with the results obtained from more popular tools we are currently using to validate the usage in the operation work. So that's all we have. Any questions?
Yeah, I have a question about the non-convergence.
Okay.
Non-convergence can have many reasons.
Yes.
So it could be that you simply don't have enough iterations, and having a longer test simply means you estimate more parameters.
Yeah.
So I just need a lot more iterations.
Right.
So then non-convergence is really not an issue.
Yeah, we pay attention to that one. So in our, like when we set the control card, we set the value really, the iterations really high. Yeah. So, yeah.
Well, there could also be conflicting constraints, in particular if you have fixed item parameters. There could be a non-identifiability thing that you simply don't get the C parameter estimated. I don't know whether it was more focused on the 3C. The 3CF is really hard to estimate.
Yeah, it's hard to
really
estimate.
one of those things where I wouldn't just say, well, yeah, more items is harder to estimate. Can be a question of the model that you're using.
Yeah, we also use the, specified priors for A, B, and C, and they are set to be the same, for different under different conditions. Yeah, and those are the sightings we use for the operational exam.
Did you check whether those priors are appropriate?
Yeah, we did.
How can you have all negative priors in all conditions good? I'm puzzled by the results, because if every condition has two no A parameters, below B parameters, there must be something wrong somewhere. You have in all conditions you have negative bias.
Right. Yeah, we noticed that. Yeah, so all conditions.
For A and for B parameters. So doesn't that mean that something is wrong, either the model specification or the software, or something is not
Yeah, something.
right?
Yeah, we noticed that it looks weird to me as well. So yeah, I think we need to conduct more studies if we want to use FlexMert for operational work. But currently, it's only for research purpose. Oh, here.
It's probably the role of a prior. You apply that prior on A and B and C.
That was my point.
Good,
So
yes.
probably not appropriate.
And prior we used our derived from our operational exam, so it's not exactly the same as the simulation data. That's one thing. And the other thing is different combination of A, B, and C parameters can actually result in very similar scheme. That's the reason why we actually presented the ICC difference first. So, you go back to the one more slide here. Actually, this is the one feature we want to really focus on. Breaking down into what A, B, and C parameters over time is leading, because A and C parameters estimate over time not compensate each other, but they have interaction with each other.
That also explains why you have results.
Yes.
Presentation. I have very simple questions about real data, real life data. How can we get the common person estimate?
It's not common person. Actually, it's the theta estimate. We computed based on the CAT items. So after CAT exam, each person has an estimate for their theta scores, right? So in the calibration, we fix that theta scores, and then to determine the IRT scale. Basically, the calibration is to identify the scale for the for IRT.
Right, yeah. So you have also the considerable items. One is the operational items that you use for scoring or estimating data, and then you have a set of items.
Pre-test.
Test items that has no
Parameter.
and you want to deliver. And here, the fixed person approach has actually several different things. Some people call it fixed effect
Model. Yeah, yeah. There are so many names for the Yeah, it's not common person.
Fix the distribution, you really use whatever MLEs,
Yeah.
that should be as if they were true. So instead of just saying, well, these are my distribution of parameters, and that I can reduce, I can
It's more like the old days conditional vector like this, where we actually. More like for rush, but conceptually, you conditionalize data and you treat it as a normal.
question is whether you more get the data that end up with the if you fix it by recording as it is operating on the deployed maximum, and that would be, well, you have already an
Yes.
estimate, well, you estimated it before. Again, I don't know.
How to calibrate concurrently.
Calibrate.
Concurrently, the whole data.
Yeah, that's the method we mentioned in the, it's one of the common, is the free calibration with the linear transformation. So what you have is you calibrate all the items in the data, and then you have two sets of parameters for the operational items, and then you compute the linear transformation constants to do. But it's still, like the CAT data, creates issues for this commonly used pretest item calibration method. Yeah.
I'm shocked by your degree of non-convergence. I'm sure it's due to the fact that one of the methods is fully Bayesian.
Mm.
Because you're fully Bayesian, Bayes theory guarantees us that if you start with the proper prior, you get the proper posterior. And that means you're also perfect.
Yeah, probably.
Even maximum likelihood should be better. I'm also shocked, but I think you should get up to 99% conversion. Over maximum likelihood.
Actually, this one is the combination of convergence and the solution stability test, and is so when I look at each of them, separately, actually convergence has much higher results than the other one. So this success rate is when we take two test results simultaneously, then it shows a little bit difference across values for each factor. So.
And the graphic in the lines are really exaggerated.
Yeah.
If you look at the y-axis, y-axis, so that's just the difference for other plots. There are different across the studied calibration methods, whether small, between big guy and the person. Actually, I have to say both work reasonably well. Not
Yeah.
well. If you really put the microscope into the result, yes, we can conclude a little better result, but between the big side and the person thing is really important.
Okay, thank you.